All right, lesson 3, operations with algebraic vectors. So what's your goals for today? I can extend my knowledge of algebraic vectors. So that's what we talked about previous lesson. So the concepts of adding and subtracting, making the connection with currently understood algebra rules. So you're going to take what we talked about yesterday, the forms of our vectors, so the unit vector form and the coordinate vector form. We're now going to add adding and subtracting into it, and we're going to follow the algebra rules. So by the time you get through the lesson and do some of the homework, you should be able to handle or be successful with that goal. So here we go. Two algebraic vectors are equal if and only if their Cartesian components are equal. So we've talked about what an equal vector is, and what that simply means is magnitude, and direction. So they point in the same direction, have the same length, is basically what that says. Here's a new term, very, very important. This one's going to come back over and over and over again. So it's good to enter that into your short-term memory for long-term use. Collinear vectors. Any two vectors that lie on the same line. They lie on the same line. So they don't have to be the same length. So I could have my first vector that looks like this, and my second vector could be a small part of it. So those would be collinear vectors. So they are on the same line, not the exact same. Okay, our operations with algebraic vectors. So scalar multiplication. So anytime you see an I and a J, you put a little hat on top since it's not easy to do with the computer. Scalar multiplication. So this is if it's in the unit vector form. Distributive law, what we taught you in grade 9, still holds true. So it'd be k times a in the x direction plus k times b in the j direction. And if it's just unit vector notation, then inside the vector notation it'd be ka and kb. Adding or subtracting. So again, you can add in some unit vector notation for me. Distributive law, we're distributing that negative sign in. So that negative has to be distributed into the bracket, and you're collecting like terms. So I'll do this in steps. So we would have AI plus B in the J direction minus CI plus D in the J direction. So now you're adding like terms. So it's the exact same as grade 9, where you're identifying, hey, these are X terms, so they can be collected together, and these are Y terms, so they can be collected together. So this becomes, in brackets, A plus D in the I direction, plus D minus C, B minus C in the J direction. So I factored out the I and the J. If you're doing it in coordinate form, this simply becomes adding your X components, or subtracting in this case, so A minus C. Oh, and the one above had a bit of a brain cramp, right? That should be A minus C. There we go. And the other one should be, whoa, big brain cramp here. B plus D. My mistake. So adding my X values together, X components together, and then adding my B components together. So you can see the two answers here are identical information-wise. So A minus C, B plus D, B plus D. They're just the forms a little bit different. So it's just like grade 9, adding like terms. So X components can be added together, Y components can be added together. So here's the example. Again, if you put some vector notation in for me. And what I'm going to do is I'm going to show you both forms here. So underneath here I'm going to squeeze in. This is also the same as 3i plus 8j. And this one, the v vector, is also equal to negative 2i plus 6j. So I'm going to use both all the way through here. So for a part, w vector, so we're doing addition. So if w is equal to 3u plus 2v. So if I do this with coordinate form first, I replace my vector u with the actual vector, 3, 8, plus 2 times the v vector, negative 2, 6. So my first step is replacement. Next, same as it would be in regular algebra, we want to do distributive law. So I would distribute the 3 into the first vector or scale it up. I'm making the v vector twice as big. I'm scaling it up. So we end up with 9 and 24 plus negative 4 and 12. Again, square brackets, that means you have vectors, so you can add like terms. So I can add my x components together. 9 plus negative 4 is 5. We'll add my y components together. 24 plus 12 is 36. So that is my resulting vector, On to b part. What happens now if w is negative 2u plus 1/2 v? For this one, I'm going to switch. I'm going to use the unit vector notation so you can see both. So negative 2, and then in brackets, 3i plus 8j plus 1/2 my v vector, negative 2i plus 6j. Again, you still have to do distributive law on both. Oops. And I have switched around brackets. That habit usually lasts for a couple of lessons. So now I have the vector. Oh, actually, I don't need. What am I doing here? It's not a vector because I'm in unit vector form. So I'll get rid of those. All right, mistake. Distributing it in, I end up with negative 6i minus 16j minus, because it's positive times a negative, minus 1i plus 3j. So now, collect like terms together. So I have negative 7i and negative 16 plus 3, negative 13j. All right, so both notations, there they are. You pick whichever one you like. Some people are going to drift one way or the other, and it'll change throughout depending, and if you go back and forth, that's also fine. I want to find the magnitude of u plus 3v. So I have to maintain these magnitude signs. So my u vector is 3, 8 plus 3 times the v vector, negative 2, 6. So I can't lose those magnitude symbols. So I get 3, 8 plus, and I'll distribute the 3 in. Keeping the magnitude symbols, I can collect like terms. So I'm going to add my x components together and my y components together. So that's 26. Now I want to find magnitude. So my next step then would be to find the magnitude of a vector. To find the magnitude of any vector, it's the square root of each component squared. And since you can't do 26 squared, or most of us can't, okay, you can leave it in that form right there. So when the number gets above, usually the rule of thumb is if it's 12 or lower, you should be able to do it a little bit further, but 26 squared, I'll let you off easy there. All right, so there is adding and subtracting with both coordinate form, okay, and adding and subtracting with unit vector form. And I end up bouncing back and forth because I find there's a time and place for each form. All right. Okay, example. Notice that we have round brackets here. Okay, round brackets mean that we're dealing with coordinates. So given the points P, Q, and R, I want you to determine the following. I want to find, and this again should have a vector symbol above, vector QP, and I want to know the magnitude of RP. So how do we find vector QP? Well, if I go to a sketch down below here, and I plot these points very, very roughly. So let's go negative 6, 1. So there is my point P. Q is negative 2. So right there, negative 1. So there's my Q. And I want to find vector QP. So I am looking for this vector right here. What I want to know, or what vector QP is, here's my starting point. I need to get a road map to get to my end point. So I need to find how far this way and how far that way I go to get from Q to P. So what I will do, if I write this in general form now, so if Q is at coordinates x1, y1. P is at coordinates x2, y2. So this distance here would be taking x2, take away x1. So I'm subtracting my p x coordinate from my q. Excuse me. The y value is going to be taking y2, take away y1, which is essentially, which is the py value, subtract the qy value. So in each case, I'm taking p and I'm subtracting q. So in order to find qp, it's equal to point p minus q. All right. We write them in as points, and this is where notation, you need to be very aware of it. So I'm subtracting points at this point. When you subtract 2 points, you end up with a vector. So -6, subtract -2, so that's like adding. -4, 1, take away -1, so that's like adding, is 2. So the vector QP is equal to -4, 2. All right, so remember that for points, when given points, oops, head minus tail will result in a vector. So the head coordinate minus the tail coordinate. Okay? That's true every time. So this is not required anymore. This is just sort of a quick show you why it works. Okay? So we don't need that anymore. So for part B then, I want to find the magnitude of point P minus point R. So the magnitude of P, -6, 1, minus, and again, it's coordinates. And I need to maintain that magnitude symbol. Now I'm going to subtract the 2 points, which will result in a vector. So it'll be -3, and 1 take away 4, also -3. Now, when I go to do the magnitude calculation, I'm finding the square root of the x component squared plus y component squared. So that's really 9 plus 9. So the square root of 18, and because there's no units, we just call it units. All right, so there is your steps. So very, very important, okay, being able to do this. So if you want to put a flag on this example, because what happens is people get on a test and they're unable to find a vector when given 2 points. So very, very important that you remember the how to do this. All right, and I'll leave it there, and we'll finish up in the next video.